So cutting parameters, a lot goes into cutting parameters. A lot of technology research and time goes to develop cutting conditions that are safe and stable and give you economic tool life. So think about your workpiece material. Think about the hardness of the material and the abrasiveness. You can have fairly soft materials that are very abrasive. And generally, the more abrasive a material is, the lower the speed. So, and just be aware, abrasiveness is sometimes the alloy is alloyed with certain elements like silica. For instance, aluminum that is more than 6% silica. You want to take a different cutting parameter approach than you would if it's less than. And then some structure of some materials is more abrasive. So get to know what material you're running and how the metallurgy, how the structure is, and that will help you with cutting parameters. So grade, obviously in grooving, grades are developed to maintain dimensional accuracy over long periods of time. You know, maintain your finish, maintain your radiuses and all those things. So interrupted cuts aren't really thought of when developing grooving or part-off systems. It's mainly thought of as a continuous process. So keep that in mind. So try to avoid interruptions, try to avoid scale or other things, you know, clean those off with another tool and then use your groover as it's intended. The dynamics of the application are very important. Stability, especially in part off and deeper applications. You know, make use of our modular systems so you can really shorten up your tool length, and just remember every millimeter counts. So short as possible to have the best stability. Cutting speed, unlike super mini or mini systems where your cutting speed is often limited by the RPM on your machine, within the GPS program, that's not usually the case. Usually you can achieve normal sort of speeds without running out of RPM since you're dealing in larger diameters. So another parameter to think about is Tmax and Dmax. So Tmax is T is short for Tfall, which is a German word for depth. And then your Dmax is your diameter max. So that's often not thought of, that there is a maximum diameter of your part. But I assure you, with tool holders, they are designed to maximize the strength and stability. So there are Dmax or diameter max constraints. So look at that, for instance, the 64T here. The maximum diameter is really dependent on the maximum depth of cut. So the depth of your groove has an effect on what diameter part you can run because the clearance is built into the insert, not necessarily the holder on that system. The other thing that's left on the table sometimes is don't forget about your entering angle. Typically grooving tools have a KR of 90 degrees. So KR is just kappa R. And so for side turning, the chip thickness is equal to the feed. But in round inserts, so if you have a radius insert, like we can have a K or a KF insert geometry, then you need to consider that you have some advantage in chip thickness by the amount of depth you take. So if you look at the diagram here, this sort of briefly explains median chip thickness. So median chip thickness is nothing more than taking the width here, and then the width sort of goes to infinitely small or zero. So you take the median thickness of your chip, and that's where the median chip thickness comes in. So you use that to take advantage of feed. So you can increase your feed and still maintain a median chip thickness that's acceptable for the forces involved, the material involved, and the cutting edge involved in the process. So you can see that 100% of the radius here is not does not have favorable chip thinning. You're very near at 100%. You're very near the feed advance equaling the chip thickness. As you approach 25%, you have an advantage because your average is much less, so you can increase your feed. So if you want to calculate what that is, there's a simple formula that's used throughout the machining industry for chip thickness. So you have HM is equal to sine of your kappa R times your feed. So your median chip thickness is equal to the sine of KR times your feed. So the first thing you have to do is figure out, based on the shape, the size of your insert, what exactly your kappa R is. And you can do that with this formula above, which is cosine inverse of 1 minus AP over R. So your depth of cut divided by R. So that proportion. So in this example, you have a 197-inch insert, so 5 millimeter. Your radius would then be 2.5 millimeter or 98 thousandths. So if you take 25%, let's say, of that radius, so 0.25 times R, then the AP is 24 thousandths and 5 tenths. We'll assume a 8 thousandths inch per rev feed, but we don't need that quite yet. Use that in the next slide. So you figure out what your kappa R is. So plug and chug, 24 thousandths divided by 98 thousandths, which is our radius. And you end up with a KR of 41.4 degrees. So 41.4 degrees. You then can take the second formula, the HM is equal to sine KR times the feed. You plug in your KR, so sine of 41.4 times your feed, and that gives you a chip thickness of 5 thousandths and 3 tenths. So if you, let's say for a given material and a given cutting edge, you know that your chip thickness can be 8 thousandths, you can then increase your feed to match that chip thickness. So you're managing, basically with chip thickness, you're managing the forces and the pressure on your cutting edge by how thick this chip is. So that's why it's important to know that. You can take a little cheat sheet here. The chart provided here has a AP 1 times R. You multiply your feed rate times 1. If you're at 75% R, you can do 1.03. And then on down to 25% of R, you can do 1.51. So you can say that for a given feed, you can multiply 1.51 times that, and that's the feed to get a given chip thickness of favorable chip thickness. The other calculation that might not be obvious, but possibly necessary, depending on your CAM system, your computer-aided manufacturing system, is how to calculate a ramp angle on a radius insert. So if we assume the ideal depth of cut is your radius times 0.25, and we use we'll use the same example inputs as before, but you first have to calculate your H, which is your depth of cut, times 25. So that gives you your depth. Then your C ramp value. So your C ramp value is what you calculated here. And then you plug and chug the numbers. And then you can take the ramp angle is just the tan inverse of your depth of cut over that C ramp value. So the C ramp value is nothing more than the distance here from the center line to where your depth is at the edge here. The ramp angle, just the cheat sheet version of that, your percent of radius. If you have 25% of your radius, your ramp angle is 21 degrees. If it's 50, it's 30, 75 is 38, and 100% it is 45 degrees. So that's your ramp angle if you're maintaining this depth. So taking the example that we have, so 98 thousandths times 250 is 24.5. Your C ramp here, your C ramp H times 2R minus H, plug and chug all your numbers there. C ramp is 0.065 inches. The ramp angle then is the inverse of that. So 98 divided by 65 and the tan inverse of that. So your ramp angle works out to be 20.7 degrees for 25% of your radius. So just something you may not use all the time, but something will have access to. The next is cutting speed. So cutting speeds can be a little intimidating, depending especially on the material. If it's a material you are familiar with, it's kind of easy. You know, okay, if I run 400 surface feet, I'm going to be in a pretty good range. So what I recommend is taking the horn values that you can find, take the max number, multiply it by 0.6, and start at that number, and then work your way up. Many times you can go outside this max number, depending on the application and depending on the cooling and how easily the chip accepts heat and removes it from the cut. So take that value, the top end value, multiply it by 0.6, and that's my best advice for cutting speeds. Same with all the other materials. So take the top end, multiply it by 0.6, and then use that number as your starting value and work your way up. So also pay attention to the minimum speed. You don't want to run too low of a speed because you can have built up edge and problems with material sticking on the cutting edge and damaging your insert.